Hello, and welcome to the next video in my series on basic statistics. Now, a few reminders before we get going. Number one, I will just be using the word stats because it's easier to say. Number two, keep in mind that these videos are geared towards individuals who are relatively new to stats. So if you have advanced study in quantitative methods, these videos are probably a bit below what you would need. However, if this is new to you or you just want to brush up on this topic, then this video is for you. And finally, number three, if you are watching this video on YouTube, please refer to the description below the video, and in the description you'll find a link to the corresponding blog post for this problem. On the blog post, you will find a download link for the very Excel file we're going to use in this video. So you can download that, open it up on your computer, and then follow right along with me step by step. So all that being said, let's go ahead and dive right in. Now this video is actually a continuation of our last chi-square video. And remember, we're looking at college enrollment over time as divided by year in school, like freshman, sophomore, junior, and senior. And we'll talk about that more here in a minute. So if you'd like a really basic refresher on the chi-square, please refer to the previous video before you watch this one. Let's go ahead and talk about our problem. Now this is the same problem we had in the last video, but let's just say that you are working in the Office of Institutional Research at a small but growing regional four-year university. Over the past 5 years, the number of undergraduate students at each level, so freshman, sophomore, junior, senior, and an unclassified group, has changed. So we have had variation in our student headcount over that time period. And here are some questions we're interested in. Even though some headcount random variation is expected, I mean, we're not going to have the exact same student headcount year to year, right? So what we want to know is the variation beyond what we would expect due to just random chance alone? So again, if I wanted to know how tall the average person is, I might go out and measure the height of 10 people, and then tomorrow I might go out and do the same thing. Do I expect that to be the same as the first day? No. Maybe I do it a third time. Do I expect that average height to be the same as the first 2 days? No. But what we're interested in is how close together or how far off is one measurement from the other. And this is what we're doing in the chi-square in terms of categorical variables. So there is some variation that's going to happen naturally. But our question is that variation in our problem beyond what we would expect due to chance alone? How can a chi-square test help us rule out that variation due to random chance alone? And finally, how can we use Excel to conduct our chi-square test? So in this video, we will spend part of our time in the actual presentation, and then we will spend the other part of our time in Excel working the problem in real time, step by step. So again, hopefully you've downloaded the file on the blog post so you can follow right along. Now here's just a quick review of the chi-square test of independence. Now if you want a more basic overview of chi-square, please refer to the previous video. The chi-square can be thought of as a test of independence. Are these two variables statistically independent, or are they related? Now it offers us nothing more than that. There's either a relationship or no relationship. We're not trying to figure out what that relationship is or describe it or anything like that. We are just using the chi-square to determine if there is a relationship or not. We have two hypotheses. We have the null hypothesis, which says that the two categorical variables are independent, so no relationship. And our alternative, which says the two categorical variables are related, so they are not independent. And remember, the chi-square is about our observed frequency of some event versus what we expect that frequency to be. So we're talking about observed versus expected, and we're dealing with frequencies or counting things. Now, is the variation between the observed and the expected frequencies minor enough to be within what we may expect due to chance alone. So again, we're going to have random chance variation, but we're using the chi-square to determine if the variation we have in our test is beyond what we'd expect from chance alone. Now in this video, we'll be using contingency tables, which is a table where one variable is along the top and its categories, and the other variable is down the left-hand side with its categories. And we're going to talk about several examples here in a second. Now we're going to be using two tables. We're going to have one contingency table for our observations, which is the data we have. And we're going to have another contingency table for what we expected in our frequencies. So oftentimes these are combined into one table, but for the purpose of this lesson, we're going to go ahead and separate them out so you can see the relationship pretty clearly. And degrees of freedom. And again, I'm not going to describe what degrees of freedom are in this video, but just keep in mind that when we have a chi-square with two variables with multiple rows and columns, the degrees of freedom are the number of columns minus 1 times the number of rows minus 1, and that equals our degrees of freedom. Now here are some examples of contingency tables I found online. Now in this table, we are looking at the relationship between the amount of work experience someone has and what position they hold. So you can see along the top we have manager, programmer, operator, system admin. So again, these are computer science or computer type positions. And then on the left-hand side we have experience ranges. So 0 to 3 years, 4 to 8 years, or more than 8 years. So we are looking at least in this table, the relationship between position and years experience. And I can tell you by looking at the bottom there, by looking at the observed value and the critical value, that there is a relationship. But again, we're going to talk about that throughout this video. Here's another contingency table, and this is a type of genetic research experiment or something like that. So we have genotype along the top, AA, AB, and BB. And then on the left-hand side, we have a case and then a control group. Now what makes a contingency table are the row totals and the column totals. So if you look at the first table on the left-hand side, we have a total for each row, so 67, 91, 88, and we have a total for each column, so manager, programmer, operator, and system admin. Same thing on our other contingency table on the right. We have row totals for case, for control, which are both 100, then we have column totals for all three genotypes. So here is a contingency table. It's 2 by 2 for whether a gale was forecasted and an actual gale was observed. So we have yes, yes, and yes, no, and so forth. Then we also have row and column totals. Now here is a contingency table for purchasing behavior. So on the left-hand side, we have the time spent on a website, and then along the top, we have the number of items purchased. And as you can see, we have totals for each row and totals for each column. Now here is a contingency table for smoking behavior. So on the left-hand side, we have different types of employees, from senior managers down through junior employees, etc. Along the top, we have level of smoking, from none all the way to level of smoking. So this is looking at the relationship between smoking behavior and employee level. And finally, we have a table for cholera inoculation. So on the left-hand side, we have whether or not the person was inoculated or not inoculated. Along the top, we have whether or not they became infected with cholera or not infected. And again, we have total and column rows. So here is our observed head count, and this is actual data from an actual university, so I did not make this up. And again, we have our class standing on the left-hand side, freshmen down through senior and unclassified. And then we have our years, 2007 through 2011. Now I will just make one caveat here. It's not all that common to use time series categories like we have years along the top in chi-squares. However, for this video, it will suffice. But just keep in mind there are certain things that come into play when we're using time series categories like the years on top. On the next couple of slides, I'm going to briefly show our graphs from our last video. I'm not going to go into each one specifically. I'll just leave it on the screen for a few seconds and then move on. So here's our simple line graph. And again, that's just enrollment over each year along the bottom. And then each class level is represented by a different color. And here is a stacked bar chart representing that data. A stacked percentage chart. A stacked area chart. A stacked percentage area chart. And finally, a spider or radar diagram. Now again, if you want to go back and look at those, just rewind the video and hit pause and you can look at it as long as you want. I go into more detail about each one in the previous video. So if you would like to know a bit more about why I use those type of graphs, please refer to the previous video. Okay, so here is our full contingency table for our observed head count. Now all I did here was added total rows and total columns. So you can see for freshmen we have a total of 2,667 over these 5 years. For sophomore we have 1,866 and so forth. And then for each year we have the total undergrad enrollments. For 2007 we had 1,469, and then by 2011 we had 1,656. The thing that makes a contingency table, or often called sometimes a crosstab table, is that when you add up the total column and the total row, it comes out to be the same thing. So if we add up all the totals in the total column, we come up with 7,715. If we add up all the years along the bottom in the total row, we also have 7,715. And that should kind of make sense, because no matter how we measure it, whether across time or through all the different grade levels, we're going to end up with the same amount of students. But that property is what allows us to do our chi-square test. Now here is our observed head count in a 3D bar graph. So again, you can see each grade level across time, and you'll notice that the freshman enrollment is always the highest, and then the sophomore is the second highest. And then oddly enough, in this data, the junior level is actually the lowest across time. Now there are some institutional reasons about why that took place at this university, but I'm not going to bore you with going into all those right now. But that's not all that uncommon for a university like this one. And then senior is the next highest. Again, so you can see how each class level relates to each other across time and grade level. So we talked about our observed head count. Now this is our expected head count. And this is our contingency table for the expected head count. Now if you notice, it has everything that the observed does except all the data in the middle, which is obviously a big part. But along the right hand side we still have total rows, and along the bottom we have total columns. Now obviously the question marks there in the middle, that's what we have to find out. And there's a very simple systematic way of finding out what we would expect in those cells given our totals and grand total. Okay, so as far as the calculation goes, this is probably the most complex slide, because it just shows you how to get each expected cell. I've color-coded everything so you can see exactly where I'm getting the numbers. Now the way to find the expected count works is you take the column total, which is there in the blue, multiply it by the row total, which is in the red, and then divide all of that by the grand total, which is the number in the bottom right. So if we look at freshmen in 2007, our row total is 2,667. We're going to multiply that by the column total, which was 1,469. So we multiply those together, and then we divide by our grand total, which was 7,715 students. And then when we go to sophomore, everything stays the same. We're still in the same column, we're still using the same grand total, but we've changed rows. So our row will now be the row total for sophomore, which is 1,866. When we go down to junior, again, the blue and the purple stay the same, but we're in a different row. So now it's 1,236. So you can see how this works. This is not that complicated. It's just row total times column total divided by grand total. Now when we go ahead and do those calculations, we have our expected head count. Now I went ahead and left these in decimal form just to make it easier. So you can see that based on our total freshmen and 2007 total and our grand total, we would expect 508 freshmen. Now for sophomore, we would expect 355, and so on and so forth down that column. As far as calculating the expected values, that's how we do it. So now let's go into Excel and figure out the rest of our expected head counts. Okay, so here we are in Excel, and as you can see, we have several tables on the left-hand side. The first table are actual observed enrollments. So for each class level on the left-hand side, and then for each year along the top. Below that, we have our expected counts. And we're going to use Excel formulas to generate those expected counts, just like we did in our PowerPoint presentation, but it will be more automated. Now below that, we're going to have our observed minus our expected. So in that table, we will actually be able to see the differences between the top two tables. And at the very bottom, we're going to have our observed minus our expected squared divided by our expected. And again, that's the last step in calculating our chi-square for each cell. Now, at different times during the video, I will actually pause it because some of the things are just too boring for you to sit and watch me do, like filling in columns and copy and pasting and things like that. All right, so let's go ahead and get started. We're going to start in our observed contingency table there at the top, and we need row and column totals. So we're going to start with the freshmen, and we want to know how many freshman students we had across all 5 years. So to do that, it's just a simple sum formula. So equals sum, open parentheses, select those 5 years, close parentheses, and hit enter. And there we go. Now, the autofill feature in Excel, if we hover over the bottom corner, it will be that black cross. We'll go ahead and drag down, and that will do the same thing for the rest of the grade levels. Now we need column totals. So this is the same concept. So equals sum. We'll select those 5 grade levels, hit enter, and there's that. Now again, we'll drag over to go ahead and autofill the rest of the columns. Now we need a grand total. So we can do the row totals there on the right-hand side, or we can use the column totals along the bottom. I'm just going to go ahead and use the row totals, which is there that goes vertically. So equals sum, and I will select those 5 cells, those parentheses, and enter. Now remember, our grand total in PowerPoint was 7,715, so this should be the same in this table. So next thing I'm going to do is I'm going to transfer over the values in the observed table to our chi-square computation columns. So I will just select the values for 2007. I'll hit Control-C to copy. Then I'll go over to the observed column, hit Control-V to paste. Now, I will do that for each year. Control-C, Control-V, Control-C, Control-V, copy, paste, then copy, and paste. Okay, so that is just the observed enrollment in column form. So each 5th cell is a different year. So next thing we want to do is calculate our expected. Okay, Now, the formula that goes in here, you really have to pay attention to because there are a couple things going on. Now remember, to calculate our expected value, we're going to be multiplying some row and column totals and then dividing that by our grand total. So let's talk about this first cell here at freshman. Now to do that, we're going to be multiplying together the total column for 2007, the total row for freshmen, multiplying those two together, and then dividing by our grand total. So how can we do that in a formula? Well, if you know how algebraic expressions work, it's pretty simple. So we're going to have equals, open parentheses, we want our column total times our row total up here, close parentheses, and then we're going to divide by our grand total, which is the cell in the lower right. And then we hit enter. And again, that's about 508 students. That's exactly what we got in the PowerPoint side of things, doing it manually. Now we're going to go back up to this cell. We want to be able to use the autofill feature, so we do not have to do that each and every time. So let's say I wanted to fill in the column below 2007. What is going to stay the same and what is going to change in our formula? Well, we know that our grand total is going to stay the same because it's always the same, 7715. Now for the 2007, we know that the column total, which is 1469, will also stay the same in our formula. The only thing that's going to change is the row total there on the right. So how can we keep certain parts of our formula stable or absolute while allowing some things to change? Well, if we go back up to the formula bar at the very top, the H11 there in the purple, that is our grand total. We want that to stay the same. So if I put the cursor after H11 and hit F4, look what happens. It makes that cell reference absolute. So it will not change as we do the autofill. Now, what else do we want to stay the same? Well, we want the column total, which is the blue, the C11, we want that to stay the same too as we drag down. So I'm going to go right after C11, hit F4, that puts the dollar signs in there, and that makes that an absolute reference. So I'll hit enter, nothing will change. But now look, when I drag down, there we go, look at that. So what it did is it kept our grand total the same, it kept our column total the same, that 1469 number, but it changed the row total, which is there in the light green, as we dragged down. Okay? So we're going to go ahead and do the same thing for 2008. So what are we going to do here? Same type of formula. Equals, open parentheses, we want to multiply that column total with the row total, which is the 2667 again, close parentheses, and then divide by our grand total. So there we go. Now again, I want to keep certain things the same. We go back up here to the formula. I want to keep our grand total the same. So hit F4. And again, I want to keep our column total the same. So I'll go after D11, hit F4. And there we go. So I'm going to go ahead and drag down. And that's the same. The next column, it's going to be the same thing. But instead of you watching me do this over and over, I'm going to go ahead and pause the video and then do those, and then we'll pick up right there. Okay, so I've gone ahead and filled in the rest of those cells with the proper formula. And again, just repeating the same pattern we did for 2007 and 2008. Now we also need totals here in these rows and columns, so equals sum. Select those cells, close parentheses, there we go. We're going to go down. Now notice what happened here. The totals are the same, and that's important. Kind of behind the scenes here, what we're talking about is proportional enrollment, versus our observed and our expected. So the totals are not going to change any. So that's a built-in check to make sure that we've done our formulas right. The totals in this column should be the same as the totals at the column up there, which they all are. Okay, so we need column totals here at the bottom. So equals sum. Select those, close parentheses. Now we're going to drag all those over. There we go. And again, this should be the same as it's up top. So let's check those real fast. Looks good. And again, we'll do our grand total in the bottom right. And there we go. Now I'm going to copy these values in the expected table over to our chi-square computation columns there on the right hand side. So I'm going to select those 5, Control Copy, Control C. Now what happened there? I made a mistake. So let's undo that. Let's say paste. Select those again. I do that all the time. We want to paste the values. Okay. So you'll see in this paste options, paste values. So I'm going to go ahead and select that. All right, so go back over here, select the next 5, Control Copy. You want to paste the values. Now again, I'm going to go ahead and pause the video and do the remainder of those, and then we'll start right back up there. Okay, so there we are with that. Now you can see in our chi-square computation columns, the observed and expected next to it refer to the same cell in our contingency table. Okay, and it's very important. So you have to make sure you get those in a proper order because they match. They represent the same data. So at the top there, for observed, we have 560. Well, that's freshman in 2007 in our top table. For expected, we have 507.8. Well, that's freshman in 2007 in our expected table. So you have to make sure that those line up correctly. Okay, so next thing we're going to do is we're going to do a simple subtraction, and we'll do it with a formula, of course, to make it easier. We want to do observed minus expected there in the middle column of our chi-square computation. So to do this, we just have equals, then we'll select the observed minus the expected next to it. That's it. Now, of course, we can just do the autofill, so it turns into the black cross there. We'll drag down, and that's that. Easy. Now, the next step of our chi-square computation is we square that. So this is observed minus expected squared. So to do this, we just do equals. We'll select the observed minus expected cell next to it. Then we'll do the little caret, which is the upward little arrow there, which is shift and then the 6 key. Then we'll square it, so 2, and that's that. So again, we're just going to drag all those down to get those values. Now we only have one more column here. So we're going to take our observed minus expected squared and divide that by our expected. So that, again, that's easy. Equals observed minus expected squared is the cell next to it. Then we're going to divide by our expected, or E, which is 2 cells over. So we hit that, and there we go. Now we can drag all the way down. And believe it or not, you have just done the basics of what a chi-square is just in a few minutes there. So you actually have right there everything you need to find the chi-square. Now I'm going to do a couple more things just so you can see each additional step. So in the observed minus expected here, we could do it, one of 2 ways. So I'm going to use a formula. I'm going to use the tables above. So to figure out this value, it will be just the observed minus the expected right there. And again, that's the same as the top of our observed minus expected in our columns there on the right. Now the cool thing is I can just drag down, okay, and again those match, and I can just repeat the process. So go over to 2008, this equals observed up there minus our expected there. That's that, and then we'll drag down. Okay, I'm going to go ahead and fill that in and pause it, and I'll be right back with you. Okay, and there we are. Again, I could have just dragged the top cell across like I did it down. It wouldn't have made a bit of a difference, but I just did it that way to make sure that everything matched up. So if we look at our middle column in our chi-square computation, our O minus E, we should see the same numbers. So 52, 13, 26, 21. Yeah, that looks good. So if we go down to the next set, starts with 7.28. Okay, there we are right here. That matches up. Everything looks good, and so on and so forth. So again, you can double check your formulas to make sure it matches the ones that are on the right-hand side. Okay, so next thing we're going to do is actually we're going to fill in our observed minus expected squared divided by expected table there on the lower left. And I'm going to do this the really easy way. I'm just going to copy and paste the ones that we figured out on the right hand side. So I'm going to hit copy, go down here, paste values. Next 5, copy, paste values. Okay, I'm going to go ahead and pause and do that, and I'll be right back with you. Okay, now that that table's filled in, we'll go ahead and do some totaling. So equals sum of the cells to the left of that. There we go. I'm going to drag down to fill. Do the same thing for the column totals. Equals sum. Select those. There we go. And then we will drag across. Now, I'm going to wait to do the grand total here. We're going to do one more step before we do that. Now, the last step on our chi-square computation is to sum the O minus E squared divided by E. So this will actually be our chi-square value. So to figure this out, it's going to be equals sum of everything in this column right here. Close parentheses, hit enter. And there we have 46.78126, so about 46.78. Now if I go over here and do a grand total, it should be the same. Equals sum. Select that column there, and there it is. So now we know we've done everything correctly. And sometimes I do these things in 2 places as a check to make sure that what I'm doing in one place is correct, because I can match it up with another thing. Okay. So guess what? We're just about done. The last thing we need to find out is our chi-square critical value here. So remember, we have a P of 0.05 and 16 degrees of freedom. So we're going to use the formula that is equals CHIINV. Okay. So that returns the inverse of the right-hand probability of the chi-square. You don't need to know what that is necessarily, but basically it's going to tell us what our threshold is for rejecting our null hypothesis. So we need 2 pieces of data to go in this. The first thing it asks us is our probability. Well, that is 0.05 or 0.05, comma, and it needs our degrees of freedom, which are 16. So we'll close that, hit enter, and that is our critical value. Now if you notice, our chi-square down here in our chi-square computation columns and in our chi-square totals down the left-hand side, it's 46.78. That is much higher than our critical value of 26.29 or 26.30. So those are the 2 things we need in order to determine what we're going to do with our hypothesis. And again, since our chi-square value in our problem is significantly more, doesn't matter how much more, but it is more than our critical value of 26.30, we have to reject our null hypothesis and conclude that these variables are related. There is some relationship between the 2. All right, so let's go back into PowerPoint and finish up our video. So here we are back from Excel, and all I've done is gone ahead and paste in the expected head counts we figured in Excel. So they are all there in the table. And again, here is our observed head count, so you can kind of see where we started. Now what I've done here is just some subtraction. I took our observed and then subtracted our expected for each cell. So you can see that for freshmen in 2007, we observed about 52 more students than we expected. Now let's say we go down to sophomores in 2009, We expected 18 more students than we observed. So if it is in red, that means our expectations were more than we observed. If it is in black, that means our observations were more than we expected. Now you can kind of see this pattern that goes through this chart, and that's why I did it. That, we have sort of a red section that runs from the lower left up to the top right. So actually that diagonal column to the middle is all red. Now there are different reasons for that. I'm not going to go into a whole lot about that in this video, but keep in mind that we did have some trends in our data over time, so that could be part of it. And there are a few other reasons as far as the institution goes. But I just wanted to show you in color and in numbers where the actual differences were. Now what is this chart? Well, if you remember from Excel, when we did our final calculation for the chi-square, the last column in our calculation was observed minus expected squared divided by our expected. So that was the last column in our chi-square calculation, and all I did was paste those into this chart. Now, just like the enrollment data, if we go to our total columns and rows there at the right-hand side and bottom, if we add all those up, so if I go to the total column on the right and I add up all those numbers, I end up with 46.78126. Now if I go along the bottom, total row there, now if I go along the total row at the bottom, if we add all those up, we come up with 46.7126. Now, if you remember from Excel, that's exactly what we found our chi-square statistic to be. So again, this is just reaffirming that our chi-square statistic in Excel was 46.78126. Now I'm going to run this slide and the next slide back and forth a few times so you can see the difference. Now this is what we expected. So when we figured out our expected contingency table, this is that graph. Now take a look at the blue columns, and then when I go to the observed, notice the change. Okay? Now I'm going to go back. Now look at the red. Here's our expected. Here's what we observed. Go back. Look at the green. There's what we expected. There's what we observed. Look at the purple for seniors. That's our expected and our observed. And finally, the blue, which is our special and classified category. That's our expected and what we observed. So the main thing there is to see that there is a difference. Now I'm actually going to make that difference explicit in the next slide. So here is our observed minus our expected for each year in each class category. Now if the bar is above 0, that means what we observed was greater than what we expected. If the bar is below 0, that means what we expected was more than what we observed. So you can see we have some very stark differences, especially as it pertains to freshmen. So in 2007, we observed way more freshmen than we expected, and in 2011, we expected many more freshmen than we actually observed. Now, if we go back and look at the enrollment data, we could probably see why that was. Now go ahead and pause the video for a second and take a look at these differences. Okay, now remember, what we're trying to figure out in the chi-square is, are these differences more than we would expect just due to random variation? So when it comes to the heart of the matter, this is what we're really trying to figure out using the chi-square. These are our differences between our observed and expected. Now we anticipate some difference just due to random chance, but are these differences we're looking at right here more than what we would expect due to chance alone? So here are our results. Now remember our problem chi-square, we generated a value of 46.78. We're going to use a p-value of 0.05, and our degrees of freedom was 4 times 4, which is 16. Now in Excel, we use our formula to generate our critical chi-square. So we put our p-value there first and then our degrees of freedom. And that generated a critical chi-square value of 26.30. Now, was our problem chi-square greater than our critical chi-square? Well, yes, it's 46.79, which is greater than our critical chi-square of 26.30. So therefore, we must reject our null hypothesis and conclude that class level and year are not independent. They are statistically related. Now in the real world, what that actually means we'd have to do more research into, but we do know that there is some relationship between these two categorical variables. Now the difference between what we expected and our observations were too great to be explained by chance alone. Okay, great. And that wraps up our second video on our chi-square test and our enrollment data. Again, thank you very much for watching, and I look forward to seeing you again next time.